Welcome to this comprehensive guide on solving first-order differential equations. In calculus and engineering, first-order differential equations appear frequently, and knowing how to recognize and solve them efficiently is crucial. Today, we'll cover the three major types of first-order differential equations: separable, linear, and exact equations. For each type, we'll learn how to, first, identify the form of the equation; second, manipulate it into a standard template; third, perform the necessary integrations or checks; and finally, arrive at the general solution. Let's begin with separable equations. Let's start with separable equations. A separable differential equation has the form dy over dx equals g of x times p of y. The key characteristic of a separable equation is that we can separate the variables, putting all terms with y on one side and all terms with x on the other side. Step 1. We rewrite the equation by dividing both sides by p of y and multiplying by dx. This gives us 1 over p of y times dy equals g of x times dx. Step 2. We integrate both sides. The integral of 1 over p of y with respect to y equals the integral of g of x with respect to x plus c. Step 3. We perform the integration symbolically to get an implicit relation between x and y. This gives us h of y equals g of x plus c. If possible, we can solve for y explicitly. Y equals h inverse of g of x plus c. Let's see a simple example. Let's work through an example of a separable equation. Dy over dx equals x times y squared. Step 1. We separate the variables by dividing both sides by y squared and multiplying by dx. This gives us dy over y squared equals x dx. Step 2. We integrate both sides. The integral of dy over y squared equals the integral of x dx. Step 3. We perform the integrations. For the left side, the integral of dy over y squared equals negative 1 over y. For the right side, the integral of x dx equals x squared over 2. So we get negative 1 over y equals x squared over 2 plus c. Step 4. We solve for y. Multiplying both sides by negative 1, we get 1 over y equals negative x squared over 2 minus c. Taking the reciprocal of both sides, our final solution is y equals negative 2 over x squared plus 2c. Where c is an arbitrary constant, we can verify this is correct by substituting back into the original equation. Now, let's move on to linear equations. Now, let's discuss linear equations. A first-order linear differential equation has the form dy over dx plus p of x times y equals q of x. What makes this equation linear is that y and its derivative appear linearly. That is, they are raised only to the first power and are not multiplied together. Step 1. To solve a linear equation, we first compute what's called an integrating factor. Mu equals e raised to the integral of p of x dx. This special function helps transform our equation into a perfect derivative. Step 2. We multiply the entire equation by this integrating factor. Mu times dy over dx plus mu times p times y equals mu times q. The left side simplifies to the derivative of mu times y. D over dx of mu times y equals mu times q. This works because the derivative of mu equals p times mu. Step 3. We integrate both sides. Mu times y equals the integral of mu times q dx plus c. Step 4. Finally, we solve for y. Y equals 1 over mu times the integral of mu times q dx plus c. Let's see an example to make this concrete. Let's work through an example of a linear equation. Y prime plus 2 over x times y equals x cubed. Here, p of x equals 2 over x, and q of x equals x cubed. Step 1. We compute the integrating factor. Mu equals e to the integral of 2 over x dx. This gives us e to the 2 times natural log of x, which simplifies to x squared. Step 2. We multiply the original equation by mu, which is x squared. X squared times y prime plus x squared times 2 over x times y equals x squared times x cubed. The left side simplifies to x squared y prime plus 2x times y, which equals d over dx of x squared y. So we get d over dx of x squared y equals x to the 5th power. Step 3. We integrate both sides. X squared y equals x to the 6th power over 6 plus c. Step 4. We solve for y. Y equals x to the 4th power over 6 plus c over x squared. We can verify this solution by substituting it back into the original differential equation. Now, let's move on to exact equations. Now, let's discuss exact equations. exact differential equations have the form m of x, y dx plus n of x, y dy equals 0. This is called an exact equation when there exists some function f of x, and y such that the total differential of f is exactly m dx plus n dysprosium. Step 1. First, we need to check if the equation is indeed exact. This is done using the following test. If the partial derivative of m with respect to y equals the partial derivative of n with respect to x, then the equation is exact. Step 2. If the equation is exact, we can recover the function f in one of two ways. Method A. Integrate m with respect to x, treating y as constant. F of x, y equals the integral of m dx plus g of y. To find g of y, we differentiate this expression with respect to y and match it to n. G prime of y equals n minus the partial derivative with respect to y of the integral of m dx. Alternatively, method B. Integrate n with respect to y, treating x as constant. F of x, y equals the integral of n dy plus h of x. To find h of x, we differentiate with respect to x and match to m. H prime of x equals m minus the partial derivative with respect to x of the integral of n dysprosium. Step 3. Once we have f, the general solution is f of x, y equals c, where c is an arbitrary constant. Let's work through an example to solidify this approach. Let's work through an example of an exact equation. 2xy plus 3, dx plus x squared plus 4y cubed, dy equals 0 here. M of x, y equals 2xy plus 3, and n of x, y equals x squared plus 4y cubed. Step 1. We check if the equation is exact by comparing partial derivatives. The partial derivative of m with respect to y is 2x. The partial derivative of n with respect to x is 2x. Since these are equal, the equation is exact. Step 2. Now we'll find the function f. Let's use method A and integrate m with respect to x. F of x, y equals the integral of 2xy plus 3 dx plus g of y. This gives us f of x, y equals x squared, y plus 3x plus g of y. To find g of y, we differentiate f with respect to y. The partial derivative of f with respect to y equals x squared plus g prime of y. This must equal n, which is x squared plus 4y cubed. So g prime of y equals 4y cubed. Integrating, we get g of y equals y to the fourth power. Therefore, f of x, y equals x squared, y plus 3x plus y to the fourth power. Step 3. The general solution is x squared y plus 3x plus y to the fourth power equals c. We can verify this is correct by taking the differential of f and confirming it matches our original equation. Let's summarize what we've learned about first-order differential equations. We've covered three major types of first-order differential equations. 1. Separable equations. dy over dx equals g of x times p of y solved by separating variables and integrating. 2. Linear equations. dy over dx plus p of x times y equals q of x solved using an integrating factor mu equals e to the integral of p dx. 3. Exact equations. M dx plus n dy equals 0 solved by finding a function f, whose differential equals m dx plus n dysprosium. If an equation doesn't fit any of these forms, there are other approaches. Try substitutions to transform it into one of these standard forms. Look for an integrating factor to make the equation exact. Use numerical methods if an analytical solution is not possible. Understanding these solution methods allows you to tackle a wide range of differential equations that arise in physics, engineering, and other fields. Thank you for watching this tutorial on first-order differential equations.